Okay, so for 1.8, it says use the definition that we got from before to prove the scalar product is distributed. That is, that r dotted with u plus v is equal to r dotted with u plus r dotted with v. And then for part B, it says if r and s are vectors that are dependent on time, prove that the product rule for differentiating products applies to r dot s. That is, and then they show us the product rule. Okay, so the first thing that we've shown from before is that r dotted with s, and we used this notation in the previous problem, is the summation over I. Let me write that a little closer to the center there, of r sub I times s sub I. And these are vectors. Good night. So, r, vector r, dotted with vector u plus v is equal to then just the summation of r sub I times u sub I plus v sub I. Okay? Just using our summation notation. Well, we don't have to prove that we can distribute with our multiplication over addition. We know that. So that's equal to Ri Ui plus, I'll put parentheses here, Ri Vi. Now the sigma notation, that can be distributed. So that is like two separate sums. So sum over I of Ri Ui plus the summation over I Ri Vi. Okay. Well, this is really just r dotted with u. And this is just r dotted with v, right? Based off our definition at the top, those are just the dot products. So this is r dotted with u plus r dotted with v. So there we go. We showed that r dotted with u plus v is equal to this. So that was part A. The dot product is distributive. But then it goes to part B. So part B, what are we doing? We're doing d by dt of r dotted with s, where r is really r sub t, and s is really s sub t. It mentions in the question that the vectors are functions of time, right? Vectors r and s are vectors that are dependent on time. So just keep that in mind. I probably am going to do the lazy notation and just write r and s, but just if you're wondering, they are functions of time. Okay, so d by dt of r dotted with s, using our definition for the dot product, is really the derivative with respect to time of, well, r dotted with s, we can use our sigma notation now. And that's really r sub I times s sub I. Right? Cool. Well, let's continue writing through this logic here. This, so I'm going to rewrite this a little bit. I'm going to pull the sigma out here, and I'm going to distribute the derivative. So what we really have is r sub I d by dt of s sub I plus s sub I d by dt r sub I. So this sigma notation can be pulled out front, and the derivative is linear, so that can also be pulled out front or distributed in. So that's all I did there. Okay, well, we can break this up now into two different sums. So we could think of it like this. Plus another sum. Okay. I might as well put these in brackets to keep up with the theme we got going on here. Okay. So what do we have? Well, so just so we can see clearly, hopefully I don't feel like I'm going too fast, but it's possible I am. We're distributing the sigma. It's hard to know online because you can't pick up on subtle cues that you would if you tutored somebody in person. Okay, so if you do have questions, you can always leave them in the comments or whatever. Cool. So what do we have? Well, we have this part. This is really just, if we were to sum this up, our r vector times ds dt, right? This is just saying we add up and multiply all our like vectors, which is really just r times ds dt. And same thing over here. These are vectors. I don't want to forget my little arrow notation. Okay. So, finally, we can say d by dt of r dotted with s gave us all this. And I'm just going to write it a little different so it matches the notation that the question gave, which was like this. Did I write my r's first? I don't remember, but this is what how they wanted it. R ds dt plus dr. I think I did that. I think I just have this backwards. So yeah. So we have r ds dt plus, and then I think they did they do dr first. Okay, that's fine. It doesn't matter. It's commutative. Dr dt times s. So there we go. All this stuff we maybe have taken for granted before, we now know for sure. So we just did a little bit of proving, and hopefully that